welcome back from the lunch. I'm Johannes and I'm working for Typefox. We are a small company in northern Germany and we develop open source frameworks for IDEs and for language engineering with DSLs, and we provide custom tailored solutions there. And in particular, the frameworks Theia and Langium are invented by us, and we do lots of contributions for them. And the reason why we develop and provide services for domain-specific languages in particular is that there are nice means for empower non-developers with tailored editors to support them for communication and exchange with other peoples, to formalize complex matters with clear languages to ensure consistency and to reduce mistakes. And these information which are formalized by these DSLs, they can be provided for existing tools. They can be transferred into databases and can be used in large software settings in companies. And in particular, this approach saves a lot of time by automatically transferring the informations with generators, interpreters, as Miro yesterday discussed and showed in detail for Langium. So when we are developing such domain-specific languages, we want to provide users with dedicated feedback regarding validations and want to give them nice feedback when they did something wrong or there are some semantic problems in the text which they wrote in their IDE, in their DSL editors. And in particular, we want to give them hints when there are some parser errors, meaning they didn't write the expected keywords, for example, or when they refer to elements which don't exist. And of course, there are some more informations on the which are quite specific for these DSLs, which cannot be formulated in grammars. For example, additional syntactic checks like unique names, but also some more information on a semantic level, which can be evaluated when the users of the DSLs are writing them with static analysis. Or the last way how to give some feedback is to simulate the information directly at runtime to give them some feedback regarding the things they specified with the DSLs. And let's look what that means in practical in a very simple example. Here's a DSL for arithmetic expressions with variables and operators and some functions. It's quite easy. And for example, a user which specifies some mathematical operations and calculations. Here they want to get feedback, for example, when they didn't follow the grammar, then they get some parser errors. The semicolon is missing here, or some keywords are missing, that are the parser errors. Of course, it's also possible to say when we assign new values, then it's fine, but if a user, for example, did that, then some cross-references are broken. That's another way of validations. Or let's say the custom checks for the language here, the names are not unique anymore, and they get some information here. And what we are interested in this talk here are some semantic issues on the type level, which can be analyzed at runtime. For example, here we specify a number variable and we assign the initial value 12. When we do something like this, then I need to restart it. And now we get the information here, for example, that false is not assignable to a variable of type number. And that's that targets the semantics of this language, but they can be analyzed with static analysis when the user is writes these expressions. So it's not necessary to simulate or to execute it. It's already visible before. And that is type checking. Here, for example, we have the assignability checks. Let's write something here. The other way around, of course, that also does not make sense. We'll get some validations regarding that. Of course, we have also some mathematical operations. For example, when we do a multiplication with false, usually it's you could define some rules how to treat it, but usually it does not make sense. You want to get some informations that you used wrong types here. So that we have the assignability, we have the operators. Another quite obvious example is in if statements. Here we need a boolean condition to decide whether we execute the block or not. When we do a multiplication here, then it's syntactically correct. We could use this expression somewhere else. When we have a number, for example, then it's totally fine. But here, obviously, we don't want to have a boolean and not a number here. So, and of course, oh, I forgot something here. The same counts when we have functions and we call functions, and the values need to fit to the parameter. So a true here does not fit to the expected number over there. And you might wonder, okay, it's obvious for you. We are all developers. It's quite expected what we want to hear. But in this talk, the perspective is, what do we need to do when we want to realize this? We have want to develop a language, and the user expected this, and then we need to develop these type checkings here. So we are focusing on the aspect of type checking with the specific validation, and the main idea is that we annotate our model and the AST with additional information about the type level. So we add type information, and then we do validations on these additional type information. We already saw for the motivation for type checking, it's really useful to provide the user of a DSL information regarding type-related constraint for assignability, subtyping, casting, and so on. In the demo later, we will see how we realize that. And another point is also to resolve cross-references. For example, in such an expression language, when we have two functions which are overloaded, so they have the same name but different input types, then we need type checking when we call such a function to decide which of the different function variants should be actually called. We need the same for generators when we process information from the DSL to write them somewhere or to derive some other code. And what is really necessary is we need some helpful error messages to show to the user when there are some type-related issues. So no or something types are wrong, it's not really helpful. The user wants to know why or which types conflict with each other. Okay, and the motivation for us to develop a new framework for type checking is that we face the problem that we want to support language engineering and modeling projects in practice with lots of customer projects and other projects, and where it's nice to have an easy starting point to do type checking. And the other motivation is that we want to reuse lots of recurring problems in type checking. For example, primitive types you have in lots of expressions, languages, functions are very common. So why do we want to develop a type checking for them for each DSL from scratch? And nowadays, everything must be in the web, so we need that as well. And therefore, we introduced Typir as a library for type checking with some provided core features for checking assignability, equality, subtyping, conversions, and so on. And to provide also some reusable types like classes, functions, primitives, and so on. In order to use such a type checking library, we provide an API for language engineers. So that's the target audience of the Typir library. It does not have a dedicated external DSLs for defining types and their relationships, but it's an API developed in TypeScript. Everything is completely open source, and we follow in general a quite pragmatic approach, which I will explain later. And we have a dedicated binding for Langium, which is a textual workbench for doing graphical for textual domain-specific languages. It's an early state. We started with it this year by Typefox, and we plan to do a first release in November. So what do I mean with pragmatic type checking? We target type checking in practical projects. So that means we don't need proofs. We don't include a rule engine or an SMTP solver. We don't support dependent types and so on. But we target to provide default implementations for recurring problems, for example, classes, functions, that you need to implement them only once. Also, some algorithmic problems are nice to have to solve them once, circular type definitions, performance cachings, stuff like that, and meaningful error messages are also not that easy to develop from scratch. And we provide a TypeScript API, which we will show later in the live demo how it looks like to realize the type-related validations we just saw. Since it's completely written in TypeScript, it's ready for the web. You can execute it in any browser thanks to JavaScript, thanks to Node.js. We can execute it on web servers, in command line applications, or with Electron, also in desktop applications like C and VS Code. It's open source from the beginning. Everything is on GitHub. We choose the MIT license, so it's commercial friendly. You can use it in closed projects. There's no need to pay anything or no contracts. You even don't need to inform anybody that you are using Typir. And we use GitHub also for discussions, and we are open for your contributions and so your ideas or fundings. Maybe you know Typefox, and we are doing a lot of language engineering with Langium. And the question is, what is the relationship between Typir and Langium? And they are completely independent from each other. That means if you have a DSL, you want to do type checking, then you import Typir, you use it as a dependency, and you can do type checking independent from the strategy how you realized the parsing of your DSL. Of course, if you have you developed your DSL with Langium, then you use Langium as a dependency, and to ease that, when you want to use both, we provide a dedicated Typir binding for Langium. And in that case, when you have a Langium DSL, then you can use the Typir Langium binding, which manages, for example, the life cycle of the Langium documents and manages the corresponding types and so on. It makes some things easier. But in general, two independent projects. We want to reuse a lot of stuff, but obviously no project, no DSL is the same in some projects. So usually you always need some custom types, some customizations of the reused stuff. And the approach which we use there is that we wrap the core functionality of type checking into services. So we describe them with interfaces and provide some default implementations for that so that you can directly use it. The nice thing is with this with the distinction between specification and implementation, that you can exchange the implementations, or if you don't want to change only a few details of the default implementation, then you override only single methods of the default implementation. The other way to customize it, so in the end it's similar like we do it in Langium. The other strategy is if you need some types which are very specific for your DSL, which are not provided by Typir, then we have a registry for kinds and types, and you can, of course, you have to implement the custom types yourself, but you can include them in Typir, and the internal type graph, for example, accepts any type nodes. Okay, let's look how the application which we saw in practice, how we do this type checking, how we realize that with Typir. So that's the view of the users, and then we switch back to the implementation view. And when we initialize the type system, of course, then we need some primitive types like booleans and numbers. We have here no strings. It's very limited, so it's called logs, but it's also restricted some more. And the idea is that we have some factors for the reusable types, which we called kinds, and then you use for the primitive kind to create a new primitive type. In this case, we need a primitive type which represent booleans, and what is important is that in our language we have the boolean type. So we see here it's called boolean, and with Typir we create these semantics types in Typir. So what we could do is we could rename it in a different way, but it still represents a boolean. So we have the types in our DSL, which are sometimes even visible to the user, like here. And we create corresponding Typir types, which can have different names. Of course, it makes sense to have them similar. And another thing what we designed is when we want to decide which nodes in our AST have which type, so the type inference, we can directly specify it here, and we can say, okay, if we have a Boolean literal, then the corresponding Typir type is this Boolean type. Or the other case is also a bit more specific when we see this Boolean keyword in our program, then also the Boolean type here should be inferred. That's the semantics here. You can structure it in a different way. You could also bind these inference rules directly, not together here with a type, so it's on your own. We do the same for numbers. And we also have voids when a function does not have a return type in this language here. We skip that for the moment. So then we have our primitive types, which is fine. Now let's look what to do with Boolean operators. For example, the plus operator should combine two number values. And we do it here. And we do it in the same way for the arithmetic operators. In each case, we create a new binary operator, which gets the name here. And it has a required signature, which looks in this way. We have on the left-hand side a number type. On the right-hand side, a number type. And the return type is also a number. And this number is the type which we created, here in line 37, which is a primitive type representing our numbers. all the other operators are in the end the same idea. For the comparisons, we also have two numbers as input, but the output is our Boolean type. Again, it's the Boolean type we created at the beginning. Yeah, logical operators deal with Boolean types. And the assign or the comparison operators compare the same type. So here we have two signatures. We can compare two numbers with each other and have a Boolean as return, or we compare two Booleans and return a Boolean for now. Later on with generics, one could think about to write that in a different way. We have some unary operators as well. The only difference is we have only one operand and not two. And we also need some more inference rules. For example, when we are calling variables, and then we need to infer the type of the variables as well. And the idea here is, okay, we look at the type of the variable first, and as an alternative, we check what is the type of the assigned value. And these are the main things here. So the functions are still missing. We are coming to that later. And that's the main idea to realize primitives and operators. Now let's look how we do that. Now we have set up the type system, but what is missing are the validations. For example, for the if, when we do something strange here, then we want to see a validation like this, and that's the code for doing that. We check if the current node in our AST is a if statement. Then we have the constraint that we want to ensure that the condition of our node that is assignable to a Boolean. If that constraint is heard, then we produce an error message which we can customize. Here in our case, conditions need to be evaluated to true. And we can also mark the elements and the property in our AST, which is a condition. So that means here only the condition got this validation, and for example, not the whole if statement is marked. So you can customize that on this level as well. We have similar validations for variable declarations in order to ensure that the initialization expression fits to the expected type. It should revert that. We are checking the assignments. That when we are doing assignments, that the type checking is done here as well. Sorry. We check the return state as well, that the return value fits to the expected return type of a function. So that's a general way how to do type checking here. And to get a small hands-on, we also have somehow a predefined print statement, and at the moment we can print everything. We can print Boolean values, we can print numbers, and maybe we have the issue that we say, okay, printing Boolean values, no, maybe we don't want to support them only numbers, then let's write another validations for that. So if we see a return statement in our AST, then we want to say that we create a constraint that, for example, we want to ensure that the value of our return statement, it should be equal to numbers, and we want to customize the validation a bit more, and want to say only as we expect numbers. Okay, so only numbers are possible to print, and okay, let's restart. It should be, oh, it should be a print. Thanks a lot. Right. And now we have it here. Only numbers are possible to print. Thanks. Maybe we could say, okay, we want to even customize it more. So the property should be the value here. And then only the value is marked here, not the whole statement. So it's possible to do some customizations on this level. For functions, we also support overloading functions. So if we have the same function twice, I just copied them, then we'll get some validations. Okay, they are not unique anymore. It's also some more advanced. So with a boolean, the type is different, the signature is different, but when you call this function, it's still not unique. Even when you rename it, it's not unique. You just need to do this. Oh, it's crashed, sorry. And for example, here we see now we have b as a boolean and the return value is a number. So multiplication of a boolean with 1, this does not fit together. And maybe we want to say, okay, an addition should be also possible for a boolean and a number. Then we go to our operator. Where is it? We want to do it, we want to customize it, and for example, we need another signature here because we want to support booleans there as well. And then we say, okay, on the left-hand side, we support booleans as well. And we see, okay, it's working here. Okay, that's the other issue. Okay, yeah, I see. And in this way, you can customize and apply your operators as you want. Of course, you could also introduce a conversion rule so that we have an implicit casting from booleans to numbers. That would be an alternative approach to do this. So the way how to define functions, it's done in a different way because the functions are specific since they depend on the way how, well, we have the function types which are defined by the user here. And so usually when we have a new AST node in our which is a function, then we create a function. So that's the idea here. And this integration is so simple thanks to the Typir binding for Langium. We skip the details for now. And the way to customize it is in this way. We have the services here, we have auto-completion for them, and then we can assign some new implementations here if we need them. So that's the way how to customize it. So we already saw the core features are provided. We saw how they work in detail. We support some types already now. For example, primitives, functions. We didn't look at classes at the moment, and we have an API to define operators, which internally are mapped to functions. You could do it in a different way, then you can customize Typir in that regard. And of course, it's an early state. We plan to release a first version 0.1 in November. So it's an early state. The code is still open. Some work is done on branches. And we plan to iteratively develop it to provide new features and to apply it in commercial projects as well. And we saw we have a nice binding for Langium, but we are open to support many other frameworks as well. For example, for Sprotty is supporting also graphical diagrams, because in the end, for example, when users connect different nodes with each other, there could also be some logic so that no wires with are allowed to use which don't make sense on a semantic level, or GLSP, or also LineWeb, which is an initiative to provide interoperability between web-based modeling and language engineering tools. So we are open there. That could be done in the future. And yeah, we have Langium. We want to are open to provide some more. And of course, there are still a lot of types missing: lambdas, generic types, enumerations types, and many more. They are on the roadmap. We plan to provide them type assertions, like you know them from TypeScript, or also some fancy stuff like cyclic type definitions, where you have classes which use a class type directly inside it as a property. Yeah, it's solvable with some lazy evaluations, but of course it makes sense to support that only once, so that you are not responsible to create it from scratch for any DSL project. And we still already have some APIs for most of the core features, but we saw, okay, we should improve them regarding performance, so there's still a lot of work going on. Let's summarize Typir and the benefits we expect from it. Main idea and motivation is to predefine lots of types which are often recurring, including some core functionalities like assignability and validations, but also providing means to customize the reuse, because if you reuse stuff and it has to be reused as it is, and there's no chance to adapt it, then often in many cases it does not make sense, because you need to customize little details usually in any project. We are aiming at built-in solutions for cyclic type definitions, also caching. We didn't talk about that, which is important for performance in huge documents, so that you are doing the type inference on your AST elements only once. On the other hand, when you are doing caching, then you need to ensure that the caches are cleared when, for example, the cached elements are still not available are not valid anymore, because you updated your document and everything was repassed. So it makes sense to have support for that. And we already saw that the error messages are more than yes or no, or error or exception, because the user wants to see what is going on. Bindings for language workbenches makes sense as well, because Typir is generic. We can do type checking on any model or object at runtime. Maybe you saw during the live demo that we have some unknown types. So unknown is a concept of TypeScript to say we don't know which type is used here. So we have no assumption how the model or the AST looked like when we are doing type checking on it. And everything together, thanks to TypeScript, it's executable in the web and in the end on any platform. And that's regarding Typir for now. Now I'm looking for your discussions, your ideas. What are your purposes? Where do you need type checking in the web? And we are still at our booth. So I'm looking for your questions now.
I actually have two questions. So first one, the first thing that comes to my mind with the comparable features which we had with Xtext was Semantics, which was a much more formal approach, not a pragmatic one, and the grammar was quite complicated. And I guess that's the reason why you made pragmatic. It covered both type checkings and interpretation. Is interpretation part of a future possible scope?
At the moment, not. But it's not that we say we don't want to do it at all. At the moment, it's not in the focus. But we already had some ideas. For example, when you already know from the Typir inference, there's a boolean constant used, and which is used, for example, in a if condition, then you directly know, even from the type checking here, it's always true or false, and then always only one branch is used, and then you can provide a dedicated message for that. So we are open for that. At the moment, we have no attempts and nothing in the code to do it. But if you have, if you're interested, then we are also happy to accept contributions from your side. Yes.
And the second question was about when you have complex grammars with grammar inheritance. The way it looks, I guess, but that may be a lucky guess, that you just have to call the method of the other grammar to do all the declarations. But have you tested it? Do you know if it works?
Which methods? Methods from?
I mean, when you have all the declarations of types and the methods and so on, in case you have inheriting grammars, is it enough to just call the other method to make all the declarations of the parent grammar first, then do your grammar declarations? Or have you tested it, or do you know if it works?
So
there's no grammar inheritance?
There is no grammar inheritance.
Oh. Okay.
Yeah, but in general, Typir is independent from Langium. So you mean the case you have multiple grammars and you are combining your DSL from several grammars to each other, and then maybe you have when you want to execute them also isolated, then you have a type checking configuration there and another there, and then you want to bring it together for one, right? That was the question.
Yeah, but I didn't notice that this wasn't existing in Langium. So.
Yeah, for Langium, you import or just copy the stuff somehow, but in general, it makes sense to think about that. We didn't experiment with that yet. But you are right, that's a good hint. We will think about that, and I guess it's possible to support that. Not at the moment, but later, yes.
It looks feasible, at least.
Yes.